Another very popular modeling technique in VHDL, and in fact, one of the most popular modeling techniques, is what we refer to as register transfer level modeling. What we do in register transfer level, or RTL for short, is we tend to model movement between large parallel blocks of data between systems, okay, using this whole model of a process that looks like a series of D flip-flops, okay? And what I mean by that is that if you think about what we talked about with the D flip-flop, you have a synchronous signal called the clock, which tells everybody when to trigger. And what happens is that there's an input that comes into these things, and there's an output. And we typically call it Q. Q is the output and D is the input. And what happens is that every time that you clock this thing, it'll grab what's on D and put it out to Q. Okay? We've seen how we use D flip-flops in finite state machines to hold the state codes. But the real power of VHDL is where you model large systems. So consider for a second that instead of just being a D input, what if we just call it data in for D in, and then instead of this, we'll just call it Q, or I don't even know what we'll call it. We'll call it like D out, for example, okay? You could actually make these wider than 1 bit. And it becomes very trivial to do this when you get into VHDL, but think of the power of what we're doing. Let's just say that you bring in 16 bits and you have 16 output bits. You could take 16 bits at a time from something, and every clock edge you could latch it in, and then you could hold it, okay? This becomes even more powerful when you think about the ability to add an enable line. So we looked at how you could use a synchronous enable line for a counter, and you could tell it only do something when you're enabled. Well, if you have a register or a set of D flip-flops, you could also have a control signal, and we could call it an enable, or you could also call it a load. You could call it kind of either of those two things. But when you put these additional control signals on there, what you do is you tell it, hey, only grab that piece of information when I tell you to. The clock's free running. You have it wired up to all of these different banks of D flip-flops, but you only tell it to latch or grab when you want it to, okay? When you group these things together, they go from being called a D flip-flop to what we call a register. Okay? A register is a group of signals that will all be grabbed at one time. Okay? What also makes a register unique is that you almost always have some sort of control signal. Okay? Some things that tells it when it's going to grab. Okay? Now, it's very powerful because if you think about a digital system, you are manipulating large amounts of data. Data is moving back and forth between the processor and memory. Data is being produced by a memory controller to address memory. Data is moving back and forth in these wide buses. Okay? Well, who is moving them back and forth? You need some sort of circuit that is going to produce the data, and you need some sort of circuit that is going to receive the data. Those things that receive and transmit these are these registers. When you do this, you transfer information between these synchronous registers, okay? And that is where you start talking about this whole notion of register, transfer, level modeling, okay? When you think about what you're going to do in VHDL, each register is a process. It is a single process. And they look very similar to each other. But you can have many processes that handle grabbing large chunks of information, producing large chunks of information, and you just build up this digital system that has all this different storage capability. It is unique, though, in terms of the way that it behaves, in that you think about these as D flip-flops. This is not what we call traditional memory. This is not a DRAM. This is not an SRAM. This is a bank of D flip-flops that have some sort of control signal associated with them. Okay? That is RTL. RTL is very popular because when you think about modeling like a computer system, you tend to model at a very high level where you're passing information back and forth between storage devices on, based upon some synchronous control signal. And that's where you get this RTL. So RTL modeling, you'll hear that term a lot when you talk about, well, what kind of modeling are you doing? Are you doing structural modeling where you're instantiating something? Are you doing behavioral modeling where you're actually doing some sort of combinational logic or some sort of finite state machine? Or are you doing RTL? RTL is just simply passing large pieces of information back and forth. But you have the ability to do stuff to the information if you want, and that's what we'll see as we go through some examples. All right, so why don't we start off with let's just model a register in VHDL and see how this looks. What you want to pay attention to is how similar this is to a D flip-flop. So I have started a project, and I have a test bench that is already created for me, and it's called Reg TB. Now let's go take a look at what we want to drive into our new system, which we're going to design and call it Reg. Okay? So here is the component declaration that I am going to build. It is going to have a clock. It is going to have a reset. It's going to have D in, and it's going to have D out. We'll start off with one that doesn't have any sort of control signal. It's just going to look like a bank of D flip-flops. But notice the big difference here. Each of the input and output ports are 8 bits wide. So this little model, just by changing this to a vector, we are now going to synthesize 8 D flip-flops. Okay? What we're going to do to test this is we'll still have a reset that resets all the D flip-flops. We'll still have a clock. But what we'll do is let's just put in some data. So let's just put in a pattern of data and see if this grabs it 8 bits at a time and pumps it out on every rising edge of a clock. So let's just put in 00 up to FF. And notice that I'm driving in the data now in hex format. So I'm going to put 8 bits in, but it's getting a little tedious. We're going to start going wide on our data, so we need to start modeling it in hex. The way you describe hex is you put the hex symbols in double quotes because they are technically vectors, and then you put in front of the quotes lowercase x. Okay? That is going to give you hex. All right, so let's begin. So the first thing I'm going to do is let's create up our new little guy here. So add to project, new file. And I'm just going to call it straight up reg. Reg is not a keyword in VHDL. Okay? So I'm allowed to call it reg. When I double click on this, I need to start dropping in the library and packages and then also the port definition. But you know what I'm going to do? You know what's better than typing? Copying and pasting. So let's just copy that out of the old test bench. And then let's come down here and let's grab the port definition and the name of it so we don't mess it up. And then I'll come in here and I'll say, okay, entity, boom. And then all I have to do is come back and say is. Then I come over to here and I'll end this puppy. And now I'm ready for the architecture. Let's go end entity. Entity. And then we'll do the architecture. Architecture. Oh my goodness. Architecture, and we'll call it reg. Arc of reg is come down here, begin, come down here, end, architecture. And at this moment, I have the shell of what should be compilable. So compile them all. The compiler has awakened, and it has told us that we are successful. All right. Now I'm going to model a register. If you think about what I'm doing, all I'm going to be doing here is the following. Let's get this picture over. Let's actually draw it like this. I am literally just going to come along and I'm going to have something that acts just like a D flip-flop where I've got D in and I've got D out. I'm going to have an asynchronous reset. I'm going to have a clock. And the only difference is that these puppies are 8 bits wide. Okay? So that's the design specification that I want to create. And so let's come over here. And now, how do I do it? Just as with the D flip-flop, I'm going to do this with a single process. So I'm going to fire this puppy up, and I'm going to start off by calling it reg proc. I do keyword process, and then I ask, what is in the sensitivity list? I look at this thing. It is sequential logic. It is nothing but D flip-flops. What is in the sensitivity list? Clock and reset. The answer to everything whenever you say it's sequential logic, clock and reset. The answer whenever you say combinational logic is all the inputs. Okay? So we are going to model sequential logic. So I do clock and reset. And this looks very similar to my D flip-flop. Let's see if it continues to. So I begin, and I want to say, what do I do first? Who's the highest priority signal in my system? Always reset. It's asynchronous. We need a way to put all the D flip-flops into a known state. So I go ahead and handle the reset condition first. So I do if reset is equal to a 0, then I am going to drive D out to something. Known value. So I'm going to say D out gets assigned. What do you want to drive it to? You almost always drive it to 0. Okay, just let's start everything as a 0. You don't have to. You could reset it and drive it all to 1s. It depends what you're trying to accomplish. But for this one, why don't we just set it to 0? So here's how I type 8 bits of hex 0. Hex, vector, 0, 0, close it. These are each 4-bit nibbles as represented as a hex character. Okay? So now we're using hex. Life is so good. Now I come along, and the second thing I want to do is handle my rising edge of a clock. We can use clock tick event and clock equals 1, but since we are using the standard logic 1164, we could also use the rising edge function. So otherwise, on the rising edge of a clock, what do you think I'm going to do? What do I do when I get a rising edge of a clock? Yeah, all I do is just say, well, the output will be driven with the input. Instead of just setting it to 0 as in the reset case, I'm just going to say D out gets assigned D in. And that is it. Otherwise, I just want to hold the last value. I just want to don't do anything. And the way you model nothing is with nothing. So you say end if, and now I'm going to say end process, and that should be it. All right, so let's take a look at how this goes. So I'm going to come along and go boom, compile, selected. One error, so you might see it. Expecting then, else if then. Okay, so now we're successful. Let's see if this thing will run. So let's go ahead and load in regtb, and it flashes. And then what we're going to do is come along and see if this guy's going. So now I'm going to go add to wave, signals in region, flash. And now I'm ready to go. Let's run this puppy for, I don't know, 200 nanoseconds and see if that's long enough. I run it. Some data's cruising along here. I'm seeing a lot of data. Okay? A lot of 1s and 0s. Okay? It comes in binary. That's very hard to read, isn't it? So I immediately am going to say, you know what? Why don't you give this to me in hex? Okay, I want hex. Ooh, look at this. Look at this. So I run it for a little bit longer. If I look at DN, it's just driving in the pattern for my test bench. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. But more importantly, look at what's happening with my output. On every rising edge of clock, it will go grab whatever was on DN, and it will grab it and store it. And then it will hold it until the next edge of clock. Okay? That is a register without any sort of synchronous control. Look at how simple it is. You know what's kind of neat about this? This is 8 bits. We went from 1 bit as a D flip-flop to 8 bits as a register, and it didn't take very much time. Okay? We could go to 128 bits pretty easily, couldn't we? I mean, it wouldn't take hardly any time at all. We could make this 1,000 bits if we wanted to. The modeling is very similar amongst all of those different sizes. In fact, the only thing that really changes is the reset condition. So how's that feel? It feels pretty good. You know what I don't have, though? I don't have that synchronous control signal that we talked about. Because this guy, this is just D flip-flops. It's just hanging around, doing a whole bunch of D flip-flops. Wouldn't it be cool if we could enable it and disable it? Well, we would have to drive in an enable signal from the test bench, but that's not that big of a deal. Why don't we do it? Why don't we change the definition of this to also have an enable line? And what we'll do is we'll only have it latch when it's enabled, and then that will allow us to have more control over the register. So I'm going to add enable to the port, and then what I'm going to do is I'm in the test bench right now, so I'm trying to add this in. So I got to have a test bench signal, and it's just going to be a single bit, standard logic. All right, and then we think about, we got to put it in the port definition, enable underscore test bench. And now I come down here and I need to think about, how do we want to enable it? Well, we could put it right here. You know what we could do? We could say, why don't you drive in DN is equal to TB, and enable is equal to a 1, and then wait. Now let's do this. Let's just pop this in here, and we'll enable it, enable it, enable it, and then how about we disable it about right here? Let's take this down, and let's skip a couple. So let's not latch in. You want to do like 3? Let's do 3. And then we'll enable it again, and we'll see if this actually does what we expect. Okay? When it's disabled, what it should do is just hold the last value. Okay? All right, so the test bench, getting the test bench up to date is probably the most time-consuming thing, because now I'll compile this. Compile selected. Enable, of course I forgot underscore TB, 17 errors. All right, whatever. All right, if I can get the down arrow going here, it'll go faster. That would be awesome. I've never heard that. Okay, compile, selected, 17 errors. And of course, it'd be even better than equals. How about putting that guy, okay? This is how I like to type. I'm a column typer. I don't like to do it all right the first time. I like to think through what I'm doing because I learn more. All right, I'm successful. On the first try. Now I come over and I'm going to add an enable to this. And this is probably going to be pretty complicated, right? In fact, not so much. Okay? It's going to be very simple because all I do is I add it up here, and now I just need to think about where it goes. Is the enable going to affect reset? No, reset blows everybody away. We always make the evaluation on what to do on a rising edge of a clock, so we don't mess with that. What we do is instead, underneath the rising edge of a clock, we say, you know what, if I get a rising edge of a clock, I'm going to check and see if enable is equal to a 1, and then I will do something such as output the input, so I'll grab the input, and then otherwise, if it's disabled, what am I going to do? I'm going to hold the last value, so I will do nothing, and I model nothing with nothing, so I just do end if. All right, let's take a look and see if this works. So now I'm going to compile this puppy, compile selected, successful. I come back to wave. I'm going to go ahead and restart the simulation. So I reset it. My enable pops in there. I'm going to add to wave signals in region. I'll nuke my prior 4 signals. And now let's pop, 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 pop. Okay, I see my enable flagging there. I don't see this in hex, so let me change this to hex. Let's go and take a look at what happened. Oh, baby. Look at this. When it's enabled, it works just as normal. It latches in 1-1, it latches in 2-2, it latches in 3-3. Not so much when you get 4-4. It's disabled, so it just holds that last value. Okay? So we've now done it. We have created a simple process that models a register that has a synchronous control signal, and we will use this quite often when we build large digital signals.